In this presentation, we are going to talk about the basic definitions of linear vector spaces. When we talked about the set of real numbers, we said that the set R2, R3, and Rn inherit the main properties of R, which are that R is closed under addition, R is closed under multiplication by a scalar, it has the zero element, it has the inverse element of addition. Even R infinity, which we're not going to be talking about in this course, which are the infinite dimensional vector spaces, all these spaces inherit the linear structure of R. And so we are going to present the basic definition of what a linear vector space is that encompasses all the properties that these sets have. A linear vector space is a set that is defined with two operations. The first operation is the addition. The second operation is the multiplication by a scalar. And basically we say that if I add two vectors, I have to get another vector. So the addition operation is on v times v and gives me a vector v. And the scalar multiplication operation is defined. If I multiply a vector by a scalar, I will get another vector. And these operations are defined and satisfy the following 8 axioms. So these are the basic axioms that are needed to define all the linear vector spaces. So for every x, y, z that are vectors, for every alpha, beta, and gamma that are scalars, we axiom first commutativity. If I add x plus y, the order is not important, it's equal to y plus x. If I add x plus y plus z, and if I do y plus z first, this is exactly equal to x plus y if I do x plus y first and then add z. The next axiom is the distributivity of vector addition over scalar multiplication. If I add two vectors, x plus y, and I multiply them by a scalar alpha, it's the same as alpha x plus alpha y. So the order is not important. The next axiom is the distributivity of scalar addition over scalar multiplication. If I add the scalar alpha and beta, and then I multiply them by the vector x, this is equal to alpha x plus beta x. The next is the compatibility of scalar multiplication and field multiplication. So if I multiply the scalar alpha and beta by the vector x, it's the same as if I multiply the scalar alpha by the vector beta x. The identity element of addition, it's the zero vector. So any linear vector space has a zero vector such that x plus the zero vector is equal to x. An inverse element of addition, every element in the linear vector space V has an inverse element denoted negative x, such that when I add x to negative x, I get the zero vector. And finally, the last axiom is the identity element of scalar multiplication. 1 multiplied by any vector x gives me the vector x. These axioms are the basic axioms required to define any of the linear vector spaces that we talked about. These axioms can be used to show additional properties for all these linear vector spaces. One of these additional properties is that the zero element is unique. And I'm going to show you the proof of this statement, that if a linear vector space has the zero vector, the zero vector has to be unique. So we know that to prove that 0 is unique, we're going to assume that there are two zero vectors. Assume that we have two zero vectors. And let's call them theta 1 and theta 2. So from the axioms, we have if x is in V, and in fact this applies to any x, for every x in V, we have x plus theta 1 is equal to x. That's the property of a zero vector. And we have x plus theta 2 is also equal to x. Now we are going to substitute theta 2 in the first equation. So we have theta 2 plus theta 1 is equal to theta 2. And we're going to substitute theta 1 in the second equation. Theta 1 plus theta 2 is equal to theta 1. And we're going to use the first axiom, and the first axiom states that theta 1 plus theta 2 is equal to theta 2 plus theta 1, which means that theta 2 is equal to theta 1. And so the zero vector is unique. Additional properties that can be proven the same way is that the negative element is unique. If I add x to y and x to z, and if both are equal, then y has to be equal to z. If I multiply 0 by any vector, I get the zero vector. And if I multiply any scalar by the zero vector, I get the zero vector. And finally, negative 1 multiplied by the vector x is equal to negative x. A very important type of subsets of linear vector spaces is subspaces. Subspaces are special types of subsets that are closed under addition and multiplication by a scalar. So we'll see what that means using an example. If we look at the space x equal r squared, the space represented here by the x's r and r. And if we consider two of its subsets, the first one is y, which is a subset of x. It's made out of this vectors small y. Y has components alpha and alpha, so it's the set of vectors whose two components are equal. Y is represented by that green line on that figure. Every point on that line represents one of the vectors with equal components. Another set is the set z, with vector small z have components beta, beta, where beta is between 0 and 1. So the red segment here represents the set z from 0, 0 to 1, 1. So any point here is represented by a vector in the set z. So z is also a subset of x. Now we will see that the set y is closed under addition and multiplication by a scalar, because if we pick any two vectors in y, pick alpha 1, an element of y, and alpha 2, another element in y, when we sum them up, alpha 1, plus alpha 2, we will get alpha 1 plus alpha 2, alpha 1 plus alpha 2, which is an element of y. So we say y is closed under addition. And you can also show y is also closed under multiplication by a scalar. And so y is a subspace. On the other hand, z is not a subspace, because I can find two vectors, for example, because if I consider the vector 0.5, plus the vector 1 and 1, both are in z, this is in z, and this is in z. This, when I sum them up, I get 1.5 and 1.5, which is not in z, and so z is not closed under addition and multiplication by a scalar, and so z is not a subspace. The formal definition: a subset y of a vector space X is called a subspace if it's closed under vector addition and scalar multiplication. A very important concept in the study of linear vector spaces is the concept of linear independence, and we're going to study this concept using an example. So the vector x 1, 4 and the vector y -2 and -8, we were looking for the combination alpha 1x plus alpha 2y. That would give me the zero vector such that alpha 1 and or alpha 2 is not equal to 0. Is it possible? Indeed. Set alpha 1 is equal to 2 and alpha 2 is equal to 1, and you will get 2, 1, 4, plus 1, negative 2, negative 8, which is equal to 2, 8, plus negative 2, negative 8. This gives me the 0 vector, and so we consider x and y to be linearly dependent, because they depend on each other linearly. If we look geometrically, the vector x and y, they are actually on the same line. X has one component, the component 1 in the horizontal direction, and the component 4 in the vertical direction. So if this is x, y on the other hand has negative 2 and negative 8, and so this is y. So you could see that they are both on the same line. They're linearly dependent. Another example, if I consider x to be 1 and 4, y to be negative 2 and 3, and if I try to write the linear combination alpha x or alpha 1x plus alpha 2y is equal to 0, this is only true if and only if alpha 1 is equal to alpha 2 is equal to 0. So the only linear combination that would give me the 0 vector is the trivial combination. If you try to visually look at x and y, you're going to find they're not on the same line. X will be something like this, and y will be negative 2 and 3. So it will be something like this. So they're not on the same line. This applies to any dimension. For example, in R3, I have these 3 vectors. Let's look at the linear combination of these vectors. If I write alpha 1x plus alpha 2y plus alpha 3z, and I try to find a combination that gives me 0, I can actually find, if I set alpha 1 is equal to 2, and alpha 2 is equal to 2 as well, and if I set alpha 3 is equal to negative 1, then I'm going to get 2, 0, 0, plus 2, 2, 2, plus negative 4, negative 2, negative 2. Indeed, this is the 0 vector, and so these 3 vectors are considered linearly dependent. They depend on each other linearly. In the last example, I have the 3 vectors x, y, and z. If I try to set alpha 1x plus alpha 2y plus alpha 3z equal to 0, so I have alpha 1, 0, 0, plus alpha 2, alpha 2, alpha 2, plus 4 alpha 3, 2 alpha 3, 2 alpha 3, negative 2 alpha 3 equal to 0. And if I try to solve this equation, you will find that alpha 1 has to be equal to 0, alpha 2, and alpha 3. All these alphas have to be 0 for this linear combination to be equal to 0, and therefore the 3 vectors are linearly independent. So the formal definition of linear independence is as follows. If I have V is a linear vector space, and I have a set of vectors B with n vectors, this is a subset of V. B is called a linearly independent set of vectors if none of the vectors can be expressed linearly in terms of the other elements in the set. Or in other words, the only linear combination that will produce the 0 vector is the trivial combination. This linear combination is equal to 0 if and only if all these multipliers are equal to 0. This is true, therefore the set B is linearly independent. Otherwise, it becomes linearly dependent. In the next section, we're going to discuss what does it mean that a space has 1 dimension, another space has 2 dimensions, or another space has 3 dimensions. The line of numbers has 1 dimension because everything in R can be written as a multiplier of 1. So everything is a multiplier of 1 because everything is multiplier of 1 vector. This is called the 1-dimensional vector space. If I look at the plane, everything can be written with 2 components, which is basically a multiplier of a vector here, I'm going to call E1, a multiplier of a vector here, I'm going to call E2, So everything in this space is actually a multiplier of E1 plus E2. And E1 and E2 happen to be linearly independent. Similarly, in R3, if I call this vector E1, if I call this vector E2, if I call this vector E3, everything in the space can be written as a linear combination of these three vectors. Any vector in R3 has a component in E1 plus a component in E2 plus a component in E3, where E1 is 1, 0, 0, E2 is 0, 1, 0, and E3 is 0, 0, 1. And so any vector space can have a basis, and the basis is defined as follows. A subset B of a linear vector space is called a basis set if first it's a set of linearly independent vectors, and every vector in V can be expressed as a linear combination of the elements of B. In other words, the vectors are linearly independent, so they satisfy this statement. The linear combination is 0 if and only if all these multipliers are 0, and any vector in V can be expressed as a linear combination of the vectors in the basis set. The dimension of a linear vector space is the number of elements in its basis set. And so a one-dimensional vector space has one element in its basis set. A two-dimensional vector space has two elements in its basis set. A three-dimensional vector space has three elements, and so on. One of the important properties of a basis set is that the elements in the vector space have a unique representation in the basis set. So what does this mean? If I have B as my basis set in the vector space V, and if I have a vector small v in that vector space, then the linear combination V equal to V1 E1 plus V2 E2 and so on plus Vn En is unique, which means these multipliers V1, V2, and Vn are unique to V. And I'm not going to go through that proof. The proof is very simple and it relies on the linear independence of the vectors in B, and I will leave it to you to think about for those who are mathematically inclined. As an example, let's try to realize what is the dimension of the space of square matrices that are 2 by 2. And so a general square matrix has form M is equal to M11, M12, M21, M22. If I consider this a linear vector space and I'm trying to find the basis set for this vector space, if you think of E1 as 1, 0, 0, and E2 as 0, 1, 0, 0, and E3 as 0, 0, 1, 0, and E4 as 0, 0, 0, 1, then the set B, which is equal to E1, E2, E3, and E4, is a linearly independent set of vectors, and also any vector or any matrix in M2 can be represented as a linear combination of these vectors as M is equal to M11 E1 plus M12 E2 plus M21 E3 plus M22 E4. Therefore, M2 has dimension 4. We're now going to check the online tool in the course website, sameradib.serb.ualberta.ca. If we click on linear algebra, linear vector spaces, basic dimensions, basic definitions, if we scroll to the bottom, in a two-dimensional vector space, I'm going to put the components of a vector E1. Its components is E11 and E12. And the components of a vector E2. The first component is E21 and the second component is E22. And then I'm going to input the components v1 and v2 of another vector v, and then the tool is going to check whether e1 and e2 are linearly dependent or not, and if they are linearly independent, it's going to express v in terms of e1 and e2. So let's look here. If e1 is 1, 1, and e2 is 1, 0, and v is 5 and 2, click evaluate, and then I get that representation that the vector v in black is equal to 2 e1, 2 of the blue, and 3 of the red. If I try a different combination, for example, -1, 1, and 1, 0, and I click evaluate, then I get a different representation. I get v can be represented as 2 of the blue and 7 of the red. Finally, if I put e1, -1, 1, and e2, for example, 2, -2, and I click evaluate, the tool is going to realize that e1 and e2 are linearly dependent, as you can see, and so they cannot form a basis set, and so I cannot express a general vector in terms of e1 and e2.